Nice. Good. We've got some good variety in here. All right. These are molecular ions. Can someone remind us why we named these ions molecular ions? No? They have the same mass as the molecule. They are the molecule, less one electron, but not less any mass. So they are an ion that will interact in a magnetic field and get pulled to a detector, but they will report a very heavy mass, the heaviest mass that will hit the detector. To form this molecular ion in black, what type of electron was lost? Sorry? A pi bond electron. To form this molecular ion, what pi bond was lost? In red. A lone pair electron was lost. And to form this molecular ion in green? A sigma electron. Are there any other plausible molecular ions for this compound?
Could any of the pi bonds within the ring technically, like it's probably less likely, but
Any and all of the pi bonds in the ring could have lost one of their electrons. So let's pick this pi bond here. By the way, aromatic rings we talk a lot more about in OChem 2. They have complete resonance all the way around. It does not matter the position of those three alternating pi bonds. They're all equivalent to each other. But let's take this resonance form and let's take this pi bond in the resonance form and let's remove one electron. That means of the two atoms sharing the two electrons, one of them is going to lose both electrons. One atom will just lose one electron. Which one loses both? Which one keeps the radical? Doesn't matter. And it would be impossible to tell because there's no difference in electronegativity. So even just breaking this one pi bond, I can say the carbon on the right keeps the radical, carbon on the left becomes a cation, or the carbon on the left keeps the radical, the carbon on the right keeps a cation. In fact, you have a homework problem like that on active, but instead of an aromatic ring, it's an alkene. And it asks you to show the molecular ion. There's more than one correct answer because it doesn't matter which way the one electron is lost and which way the radical is placed. How could there be? Now up here in black, we said the radical ended up on oxygen and the cation on carbon when the pi bond was lost from the carbonyl. Okay? Because oxygen is more electronegative, that remaining electron is more likely to get pulled towards it. Yeah? What about with cyclohexane? Yeah. It's hard to count the carbons when there's a bond in there that is a one electron bond. I thought maybe this was only 5 carbons, but actually this is an end. And this is an end. So that's 1, 2, 3, 4, 5, 6. And those two ends are held together by one electron. Are there any other molecular ions I could have made for cyclohexane? Why not? Why are there so many possibilities for benzoic acid, but only one possibility for cyclohexane? Cyclohexane is less complex. Anybody have something to add to that? Britton? Yeah, benzoic acid has tons of pi bonds, tons of lone pairs. In fact, we showed a lone pair being lost from the carbonyl oxygen, but we could have just as readily lost a lone pair from the carboxyl oxygen, the OH of the carboxylic acid. That would have been a distinct molecular ion as well, a different place where a lone pair was pulled off from. And cyclohexane really only has two bond types: carbon to carbon, all symmetric all the way around the ring, and carbon to hydrogen. But nobody showed a carbon to hydrogen bond being lost, having an electron lost. So there is one other structure that cyclohexane could show in forming a molecular ion, and that's if a CH sigma electron is lost. Deal?
So in that, would that mean that carbon would have to lose the electron though? Because we talked about before it didn't matter which carbon had the radical. The carbon has to have it, or the hydrogen has to have the radical.
Actually, not quite. Here, we lost a pi bond. So we preserved the sigma bond between the carbons, and now we're just wondering, where should the remaining pi electron go? Should it go to one carbon or the other? But here, we're not losing a pi electron, we're losing a sigma electron. So actually, both atoms keep the remaining radical electron, which means that the positive charge is not localized on an atom. The positive charge is localized on that bonding area. And this is actually such a unique structure. It's not very common that you predict a structure that has a one electron covalent bond, which is why it looks so strange. It's hard to comprehend. It's also not very stable. And that's where we're going to dive into today. We're going to talk about what happens if that strange type of structure does form and how it leads to more signals. Before I do that, I'm just uploading our last document to Canvas. So our worksheet for today is on there. And I'm going to project this. I really got to figure out. Oh, I can't. I did a bad thing. Oh, no. Okay. Do I start over? 7 minutes in. My little mic thing is taking up my HDMI port. Oh no, I have this. Whew. Technology, man. Can't live with it. That's it. All right. So we looked at these molecular ions for benzoic acid and cyclohexane. Now, let's talk about daughter ions. I'll be honest, I can't really explain to you the gendered language that chemists decided. If they were going to call them daughter ions, then I feel like they should have called these mother ions instead of molecular ions. But daughter ions form when a molecule fragments. Now, for example, I want to consider cyclohexane. If cyclohexane really did form this molecular ion, and those atoms, carbon and hydrogen, are held together by one electron, it's not likely that they'll stay together. It's very possible that the two fragments, hydrogen and the rest of the molecule, drift apart from each other. There's not a lot holding them together. So a question arises, which is, which species will take the radical with it, and which keeps the cation? Remember that molecular ions were called radical cations because they contained both radicals and cations. But two things can happen from this structure. One of them is the rest of the ring keeps the positive charge, and the hydrogen drifts off as a radical. If you remember my diagram from last class in our schematic, as these molecules are traveling through the electron beam in a straight line, radicals will keep traveling in a straight line and go to the waste, whereas the cations get pulled by the magnetic field down to the detector. If there's a radical cation, the cation part of that structure pulls it to the detector. But here, I have fragmented my molecule. This is a very simple fragmentation. It's just carbon and hydrogen fragmenting. But now my hydrogen is a radical, unaffected by the magnetic field, flies off into the waste. And my cation is pulled by the detector. But in another scenario, the carbon keeps the radical, and the hydrogen ion is pulled to the detector. By the way, this is the only part of OChem that you'll really need a calculator for. And once you get good at approximating some of the values, you don't really need the calculator either. This molecule, cyclohexane, has a chemical formula C6H12, so a molecular mass of 84. We see that on the mass spectrum, that it has this molecular ion signal at 84 mass to charge, because it has a mass of 84 and a charge of 1. I do want to point out that there's a signal just to the right of it. That's called an M+1 signal, and it often results because of the small amount of carbon-13 and hydrogen-2 that's in the environment. For every 99 carbon atoms that weigh mass 12, there is one carbon atom that weighs mass 13, and that adds up eventually into these louder signals, heavier than the actual molecular ion, isotopic clusters. But this signal just below it is actually our M-1 signal. That is the mass of the molecule less one atomic mass unit. Why does it weigh one atomic mass unit less than the molecule? Hydrogen has been lost. So we refer to the signal by the mass of the molecule minus the mass of the radical that is not being detected. This fragment shows up at 83 mass to charge, 83 m per z. In the other scenario, where the carbon keeps the radical and hydrogen becomes an ion, this would show up at a signal of 1 mass to charge. What would we call the name of that cation? What would we name that daughter ion? How much mass has been lost? A lot? 83. This is the M-83 signal. And actually, you'll notice a lot of our spectra don't go below 10. So we're not actively analyzing for those hydrogen ions that can be produced. But in theory, it's there. Now, this is kind of a strange molecule. It's so simple. It's just carbon and hydrogen. As soon as we get more complicated functional groups, we start to predict the daughter ion formations by alpha cleavage. If we imagine a structure, here I've just got a simple 4-carbon chain and some group X attached to it. If this is my function, actually instead of X, I'll just call this FG to abbreviate what? Functional group. If I've got a carbon bonded to a functional group, a carbon that is now a functional group carbon, we'll often call this the alpha carbon. That's a carbon of interest because it has some functionality on it. And what we often find is that the bonds cleave, we form fragments at a bond to this alpha group. I could have alpha cleavage on the right. That would leave me with my alpha carbon bonded to the functional group plus this other fragment. And the reason that we see this is because if the cation forms on that alpha carbon, oftentimes the functional group has some way of stabilizing that. The functional group might be able to contribute through resonance. The functional group might be able to contribute through induction, pushing electron density to protect that positive charge and stabilize it, making it more likely to form.
So do you put an X where you're referring to alpha always like that, or are you just like showing an example?
This
Yeah.
is not X.
Oh, okay.
It's alpha.
Oh, it is alpha. Okay, never mind. I thought you were just doing one thing.
But I can see how it looks like that.
Okay.
Right. Thanks for bringing that up.
Yeah. Can you explain how you define the alpha carbon again?
It is part of a functional group. It's the carbon bonded to the OH that makes it alcohol. It's the carbon bonded to the amine, that the nitrogen, that makes it an amine. It's the carbonyl carbon, the CO double bond carbon.
And if a molecule has multiple?
Well, now you've got multiple places where alpha cleavage might happen. So let's take this example with 1-butanol. I'm going to put this kind of in the middle of my structure, and we're going to look at a number of different things that can happen. First of all, we know how we could predict the molecular ion formation. 1-butanol has a molecular ion. I don't know. I think it's at 72, but it looks like it's showing up at 73, which is actually, I think it's at 74, and we're seeing the M-1 showing up more clearly. I didn't keep the molecular mass on there. We know how we could form the molecular ion. It would be by losing a lone pair from the oxygen. That would be the easiest and most likely way to form a molecular ion. But the daughter ions that can form here are a bit unlimited. So let's start by looking at alpha cleavage. First, my alpha carbon is right there connected to the alcohol. That's alpha. In green, I want to consider the cleavage that could happen to the right of the alpha carbon, cleaving the bond between alpha and the methyl group. If I cleave this bond, I should be able to predict two scenarios. One where the alpha carbon takes the positive charge, and one where the alpha carbon takes the radical. I'm fragmenting at this bond, and there's two possibilities with each fragmentation. The leftovers would be a methyl radical or a methyl cation. How much does a methyl group weigh? What's carbon's mass? 12 plus 3. So a methyl group has a simple mass of 15. In this first possibility of fragmentation, can you tell me which fragment reaches the detector and registers as a mass to charge? the one that has a charge, registers at the detector. So this reaches the detector. We'll call it the M-15 signal because I've lost a methyl group. If the mass of this is 74, the molecular mass of 2-butanol is 74, then 74 minus 15 tells me I should predict a signal at 59 mass to charge. In the other situation, where in the other possible fragmentation, where the alpha carbon keeps the radical, it's my M-59 signal that shows up at a mass to charge of 15. Do I see a mass to charge of 15? I do. It's tiny. It doesn't form very often. When this alpha bond breaks, when this alpha cleavage occurs, it more often results in the positive charge being held by the alpha carbon. Less often is the positive charge held by the methyl group. I don't see that signal happening quite as much. By the way, this spectrum is reproducible. This is from an online source, but if you took the compound and ran it through our mass spec across the hall, you would get that same spectrum, same relative intensities of all of the peaks. Why is it so consistent? Because we're analyzing a really good sample size, just a few 100 million molecules. This is repeatable observations. It will always fragment in these consistent ways. And it's based on stability. Why is this so stable? I want to take it over here. It's because of resonance. The oxygen holds a lone pair adjacent to an empty orbital, that positive charge. Oxygen donates to that empty orbital, takes the positive charge onto itself by giving up some of its electrons. Resonance stabilizes this fragment, which makes it more likely to form, which means that it shows up more often. Can you tell me which of those two resonance forms is more stable? Unit 1. There's 3 rules. We want to minimize charge. Doesn't apply. We want to maximize octets. Does apply. Which of these 2 forms maximizes octets? The one on the right. Carbon with a positive charge has 6 electrons. Oxygen with a positive charge here still has 8 electrons. Remember, draw in those lone pairs and prove to yourself that oxygen kept 8 electrons. Just because it has a positive charge doesn't mean that it doesn't have an octet. Here it does have an octet. So this is actually more favorable, and it's because of that alpha cleavage that this can form to stabilize that fragment, causing it to form more often. Let's consider alpha cleavage on the other side. If I cleave the alpha to carbon bond on the left, I once again get 2 options. I want you guys to predict the 2 combinations of radical and cation. Figure out their masses and report them as M minus the mass of the radical. I'll come around to answer questions as you do this. Good start. Where's this dot?
This one.
Is it on a specific atom?
It's on the thing, isn't it? I don't know.
If
Oh,
we're
but
breaking,
it would be here then, right?
good, good. And then I want you to think about that same thing with the charges. It's not out somewhere, it's at a specific spot. Is this positive charge on this atom?
No, it's on this one here,
Let's show it there if we can then, so that we highlight which one it is.
and then this would be here as well.
Good. Now,
And then
I think you've got too many carbons.
I do.
When I break this bond,
That
I should have
carbon
2 on the
stays
left,
there.
2 on the right. I should only have 4 carbons. 1, 2, 3, 4, 5.
Wait, but why does that? Your math is right, but that doesn't make sense.
Mm-hmm. Yeah, I think you've double counted this carbon.
Oh,
When I
yeah.
break that bond, I should get this. That
So
looks
I need
right.
to not draw this and just
And then I should get this, which is just a line. Maybe it's easier not to use bond line here because it's so short, and just to use CH2CH3. Good, great. And then think about the radical here.
So it would be.
This should be CH2, not
Oh.
C2. That's okay.
I meant to.
Yeah, yeah.
And then it would be. Oh, it would just be.
Right. And this version has the radical.
Yeah, yeah.
Cation radical, cation radical. Good.
This first one.
What's your what?
Oh, sorry. This
Yeah.
is this a CH3?
It's not. It's actually this CH2.
Oh, CH2. This one.
This
Oh.
CH3 is still there, which is why it might be easier not to do bond line and to take that short CH2CH3 group and actually spell it out. Great. Good job. Now, once you've predicted those structures, can you label the ions? Can you predict their masses?
Plus the carbon bond, when it loses this bond, it creates the positive on that one. CH2 and CH3 as well. 'Cause the
Well, it
atoms
used
have
to
that
be,
order.
but we're trying to show when that bond breaks, which means it should be just that.
And then a
CH3 to the alpha carbon to the OH.
yeah. And then this one.
So it's not this?
Get rid of the CH2 part, just get rid of that.
CH2,
Now, this is one fragment. The other fragment is this, CH2, CH3.
connects to the CH2.
Oh, wait, did I break it wrong?
No, you broke it right.
Oh,
That's what I would.
This is one fragment.
and then that's the other.
Now draw me the other one.
Oh, okay.
Yeah.
Great work. Yep, that's it.
That's it? Oh.
Which is why it might be easier to write it as CH2, CH3. Good, Perla.
Are these numbers right?
Yes.
So I did it right?
Mm-hmm. Great work.
16?
So I think
Nice box.
Hamza, you've
Yeah.
placed your positive charge on the wrong carbon. It looks like you've put it on the CH3, but it should actually be on the alpha
I see.
right here.
Lock in the middle.
Yep.
Okay.
And then this fragment and this fragment, these two, are what you get from that red bond. There's not another CH2. So this doesn't exist,
Okay.
just these two.
I see. Okay. Thank you.
Yep.
Wait, so do you count these as CH3?
Forgot your OH. Yeah, you've just written it two different ways. You've drawn it in its bond line, and then you wrote it out, but you didn't actually put the radical or the cation when you wrote it out. But most people were getting confused by just drawing a stick and then trying to put a dot on it. So instead of drawing a stick, use the condensed molecular structure. Kind of, you know how in my green example, I didn't give you a dot to represent the one carbon, because that's confusing. Instead, I gave you the condensed form, CH3.
How do you know which
I don't know.
Okay, so you,
All of it happens.
oh,
If it shows up on the spectrum, it happened.
like, okay,
And
do you, like,
I think you're asking how can you predict the probability of it happening?
like if it's gonna be in my molecular INR, if it's gonna have, yeah, like alpha cleavage, or if it's
So remember that you are analyzing 500 million molecules going through this. So 60 million of them formed a specific structure. Another 10 million formed something. 1 million only formed the M minus 53 signal, right? Yeah, yeah. So on my spectrum, you see that the units are M per Z. M stands for what? Z stands for charge. So we're saying that Z is charge, which in theory means if I do get a possible structure that has lost 2 electrons instead of just 1, and now I have a 2+ charge, that mass gets pulled by the magnetic field even more strongly because it has a stronger charge to it. So it hits the detector at mass divided by 2. It looks a little bit weird. I don't get into those scenarios with you guys where you get mass divided by 2. For everything that we'll consider, it's mass divided by 1, which is basically just mass. But it's a reminder that the radicals don't hit the detector. And you'll notice this when you take your practice exam. I ask questions on mass spec that are as simple as, which of the following gave the M-15 signal? And sometimes it's comparing the radical version versus the cation version so that you recognize it's the cation that hits the detector, not the radical. So our options here, this is where I was telling you guys as I went around, maybe don't draw that stick with the dot and the cation. Maybe instead you want to show it as CH3CH2 with a dot and CH3CH2 with a cation, just to make it make more sense to you. And then on the other side, I think most of you didn't have any trouble keeping that in its bond line form. 2 possibilities when that alpha bond is cleaved, which means 2 possible cations that will reach the detector. What is the mass for this cation? Or what would be the name of its signal? Well, CH3 is 15. How much is CH2? 14. Which means my ethyl chain has a mass of 29. So this is the molecule minus 29 signal. 74 minus 29, 74 to 54, 54 to 43. Yeah? M equals 43 mass to charge. Let's look at 43. I'll trust you. Yeah. I'm sure I did it wrong. Thank you. Let's look at 45. I would have gotten real confused. Ooh, 45. Oh, I'm realizing something I forgot to teach you that was already on the last page. 45 is the tallest signal on the spectrum. We call that the base peak. So let's define that. I should have given that to you on the last page. The base peak arises from the most abundant fragment, which oftentimes tells you something about the molecule's stability. It helps you predict what is going to be stable about the molecule. So if this alpha cleavage ion was M minus 29 with a mass of 45, then the other possibility is the M minus 49 and should show up at a mass to charge of 29. Do I see 29? I do, but it's not very big. So in both of our alpha cleavages, we saw that the alpha cleavage to give the cation to the alpha carbon happened more often, confirming that that resonance stabilization promotes the alpha carbon keeping the positive charge, making it more likely for that bond to cleave. Now we're finding the base peak says that this cleavage happens more often than any other type of cleavage. And it happens in this direction rather than the radical and the cation swapping because of that resonance stabilization. We'll see the same thing with carbonyls. We see the same thing with halogens, with nitrogens. We see something similar with our alkenes and aromatic rings. Cleaving at the alpha position allows for resonance stabilization, making it a more abundant fragment. Okay.
I have some questions.
Tell me.
Okay, so starting back,
Oh, actually, while you think about that, I want to tell you this correlation table I gave you. I actually don't call it a correlation table. I call it examples. And that's because there are different fragments that can give the same masses. So you'll notice that a propyl chain is the same mass as a 2-carbon carbonyl chain. Same mass, different combination of elements. That is a challenging part in mass spectrometry. Same thing at mass of 57, a tert-butyl group and a 3-carbon carbonyl chain give the same mass. So there are some peaks that can be useful to ascertain information about, and other peaks that are challenging to ascertain information about. In general, though, I don't give this to you on your midterm or final because you don't need it as much to be able to answer the questions on mass spec that I ask you. It's a good visual to help you understand what will show up where, but it's not as useful as the NMR and the IR tables. Jordan?
okay, so with alpha cleavage, we're identifying the broader ions, and so to do that you have to do both sides of the alpha carbon.
Yeah,
Okay,
good.
and then for each of those, so for the first example, you took the mass of the entire molecule, which you calculated was 74.
That's right.
And then you calculated the mass of the particle that was cleaved off, and that gave you your first signal at 59.
Yes.
And you put it under that one because the one with the radical is not going to hit the detector.
That's right.
That one hits the detector.
The fragment holding the radical doesn't get pulled by the magnet, doesn't reach the detector, but this cation does.
Okay, so then for the other option,
Now the cation that hits the detector has a different mass. And the detector knows that it has a different mass.
wait, can you explain the math for that one though? It's like not making sense.
Sure. Here, I lost a group that weighed 15. So this fragment that reaches the detector is the molecule less 15. If the cation and radical swapped, this will show up with a mass of 15. That is the molecule less everything else, 59.
Okay.
It gets a little ridiculous to look at a big number. Like earlier, I had N minus 83, and the molecule weighs 84. Great. That's the mass of the molecule minus the entire molecule except for a hydrogen. Yeah? Gets a little ridiculous.
As far as base peak goes, can we assume that the highest signal is always the most stable? So for that one, the 59 is higher than the 15, so we can assume it's more stable and more abundant.
Yeah. So let's look back at our very first mass spectrum. What is the base peak signal? Allie? At 29? No, I don't think so. You're talking about the very first one? Okay. 2-butanone. What is the most abundant signal? What's the base peak? At 43? 43 mass per charge, aka the M-29 signal. And you'll notice that that is a fragment that is resonance stabilized. What is the other resonance form? It happened from alpha cleavage. The alpha group on the right was cleaved off. I started with this ketone structure. I cleaved off the group on the right, and that structure has resonance with the oxygen that stabilizes it. I lost an ethyl chain, M-29. So oftentimes, yes, the base peak is the most stable fragment, but not always. I wish it were more consistent. Sometimes the base peak is really challenging to ascertain. Rings especially can go through some strange structural reconfigurations when they get ionized, so we're not getting into that. There's some other things about fragmentation I wanted to touch on. Briefly, they don't come up much for us. I think you'll see them on active a little, and you might have seen them in the textbook. It has to do with alpha cleavage, but it's this idea that one, nitrogen groups often bring an additional hydrogen to the structure relative to what carbon or oxygen would bring. And one additional hydrogen increases the molecular mass by just 1. Most organic molecules, oddly enough, have a molecular mass that's even. But with nitrogen in the picture, it often has a molecular mass that's odd. That's for an advanced spectroscopy course, so you won't have to analyze any of that information. But if I have a primary amine group, I often get a signal that is M minus ammonia. The NH2 steals another hydrogen from the structure. So that's 14 and 3, 17. This often leads to an M minus 17 signal. When I have an alcohol on the structure, I often lose water, which means that I can see an M minus 18 signal, indicating that the alcohol has left and also ripped another hydrogen off of the structure somewhere else. So these types of signals can be indicative of these groups. M minus 17 might indicate that we've got an amine. M minus 18 might indicate that we've got an alcohol. There's one last component here to analyzing mass spec, and then we're going to move into IR. Isotopic clusters. I already mentioned this briefly when I pointed out that most molecular ion signals have a second signal just higher than it, resulting from the 1% of carbon that has one atomic mass unit higher than all of the others. And you'll notice there's actually a lot of other fragments in all these spectra that we really didn't get to. But bromine and chlorine introduce very unique isotopic clusters. Bromine consists of 2 primary isotopes, bromine 79 and bromine 81. This is 51% of all bromine has mass 79. 49% of all bromine has mass 81. So on average, bromine has a mass just under 80 grams per mole. But when I'm analyzing structures, I'm not averaging what hits the detector. I'm looking at every specific mass. This leads to an isotopic cluster. If this is my molecular ion, on the left, that results from bromine 79 in the structure, which occurs 51% of the time. And just 2 mass units heavier, we report an M+2 signal. It's 2 mass units higher than the molecular mass, resulting from bromine 81 in the structure 49% of the time. We call this a 1-to-1 isotopic cluster, but you can see that it's not actually 1-to-1. It's 51 to 49. But the height of those 2 peaks that differ by only 2 mass units is almost equivalent. Can you identify any 1-to-1 clusters in this mass spectrum for tert-butyl bromide? What do you see? No isotopic clusters? Would be strange because there is a bromine. And for every 100 atoms of bromine, 51 of those atoms weigh 79. 49 of those atoms, did I say that right? For every 100 atoms, 51 weigh less, 49 weigh more. 2 isotopic clusters? Where do you see them?
Like 28 or 27 and 28 or 9.
So like here?
Yeah, and then on 39 and 41.
So 27, 29 are 2 mass units apart.
Okay.
Do they look 1-to-1?
No.
They don't look 1-to-1. So it's likely not the result of bromine. Also, bromine does not weigh 27 or 29. Even if these were just the bromine atoms and not connected to the rest of the molecule, the lowest mass that they could have is 79 and 81. And actually, let's look there, 79 and 81. You know what? It rises above the baseline. It's non-zero. So those could be the atoms of bromine that have been cleaved off of the molecule. But it seems like bromine 79 cation and bromine 81 cation don't form very often. If anything, they probably cleave and take the radical because they're more electronegative. Where else were you looking? Here?
Yeah.
Yeah, another one that's not quite 1-to-1. 121 and 122. It's very small, which tells us that it does not happen very often. In fact, I don't believe that this is even the molecular ion. This molecule weighs 15 plus 15 plus 15, 45, plus 12, 57. We know that from the correlation table. 57 plus 79. Oh, that would be 121. No, the math doesn't make sense there, does it? Hey Siri, what's 57 plus 79? 128? Bummer. 136. 136 makes more sense. Okay, so if this has a molecular ion, really the most likely form is when bromine loses a lone pair electron. This has a mass to charge of 136, which means that our spectrum never picked it up. That molecular ion doesn't really form, and it never shows up. So what is this signal at 121? Well, if the molecular ion is 136, that would be the mass less 15. What would that structure look like? Alpha cleavage of a methyl group. If I lost a methyl radical and my alpha carbon takes on the positive charge, the bromine can actually stabilize that through resonance. If you're not happy with looking at that structure, this is the other resonance form. This has a mass of 121 mass per charge. So then why do I see a signal at 123? It's 121 if the bromine is 79 mass units. It's 123 if the bromine is 81 mass units. And that happens about every other time. So for 500 million molecules that come through, 250 million had one bromine, 250 million had the other. What's our base peak here? Looks like 57, 60, 59, 58, 57. What does your correlation table say has a mass of 57 mass per charge? Tert-butyl. So this is the M minus what? Signal. M minus 79, which results from the loss of bromine. And why do we say 79 when the periodic table reports it as 79.9? Because we are picking one of the two isotopes. We're not seeing an average atomic mass here. We're picking the lower atomic isotope, the lower massed isotope, to set as our reference, and we use the higher massed isotope as the M+2. So my molecular ion, 136, minus 79, leaves me with this tert-butyl cation. What's the radical that generates? The bromine radical. But it's the tert-butyl ion that gives me that mass at 57 mass per charge. Can you tell me why my base peak does not have a 1-to-1 isotopic cluster? That base peak is formed by a structure that does not have bromine. There's no bromine when this reaches the detector. So there's no 1-to-1 odds of bromine having one mass or the other, right? Do you know what the masses are for the chlorine isotopes? If I told you that chlorine's average atomic mass is 35.45, could you guess what the masses of the chlorine isotopes are? 35.45. It's actually 35 and 37. There's a lot less 37. Here, we see 75% of the isotopes weigh 35, and only 25% of the isotopes weigh 37. And this gives us a 3-to-1 isotopic cluster. If bromine is a part of my sample, I can tell by the 1-to-1 cluster. If chlorine is a part of my sample, I can tell by the 3-to-1 cluster. Now the compound that I've given you actually has more than one chlorine. It has two. So now we have to factor in, what are the odds that both chlorines are mass 35? What are the odds that both chlorines are mass 37? And what are the odds that I have one bromine mass 35 and one mass 37? I have two bromines, so I get a more complex isotopic cluster. Can you see that more complex structure? At our molecular ion here, 146, I have a signal that is maybe 2/3 the height, and then another signal that is maybe 1/3 that height, although it looks a lot less than 1/3 that height. This is that more complex isotopic cluster. Do you see any evidence of a normal 3-to-1 isotopic cluster?
Should it be like
110. I think, yeah, that is 110. 111 and 113, a normal 3-to-1 isotopic cluster. Can we predict the structure of the fragment that gives this signal? I want to see the 111, 113 mass per charge signal. If my molecular mass, we should do this. Benzene itself weighs 78 minus 2 hydrogens lost is 76, plus 35 plus 35. So 36 plus 70, 106? Well, that doesn't make any sense, does it? I should have taken a bigger screenshot. Why is its signal showing up at 140 something? No, it weighs 78 minus 2. 76. No, 76 plus 70. I don't know what I was saying. Sorry. 76 plus 70, 130, 146. Okay, so we have a molecular mass of 146. What mass do I need to lose to go from 146 down to 111? 35, which is the mass of chlorine. M minus 35, that's the loss of chlorine. Which chlorine do I lose? Doesn't matter. Either way, I need to put a carbon with a positive charge because that carbon-chlorine bond has just been cleaved. This fragment still has one chlorine. So 75% of the time, the chlorine is 35. 25% of the time, the chlorine is 37. So when this fragment forms, I still get a 3-to-1 isotopic cluster. And now there's more complexity where this ring can go through reconfiguration and it can actually lose both of its chlorines. We're not going to look at that so much. Jordan?
Can you, because the base peak, sorry, is at 146.
Yes. Oh, I'm sorry. I was just getting ahead and I was eager to move on.
Explain why that is it
The base peak is at 146. Here's our structure.
mass is at 146, so nothing happened to it?
Say that again.
Like the mass of the entire thing is 146.
That's right.
So it was less likely to react
Yeah, well,
or to lose that?
less likely to fragment than it is to just stay entirely together.
Okay, so just the entire molecule hit that rate.
So this is a rare scenario, because we didn't see it with any of our other spectra, a rare scenario where the molecular ion is the base peak. They don't need to be the same, but they can be the same. This time the most stable fragment, the one that formed the most often, was the molecular ion. How many different ways could you draw a molecular ion for this? A lot of different ways. I've got 6 total lone pairs across the 2 chlorines that I could steal. And then I've got those 3 pi bonds in the ring. And I've got this ability for resonance. If one of these pi bonds breaks, the chlorines can actually help contribute to resonance. So it's not surprising that the molecular ion is the most stable here rather than cleaving some of the bonds. But that was a really good observation. The base peak is the molecular ion peak. All right, let's take a break. 5 minutes. Come back in here so we can plow through IR. I'm going to hand out the IR packets now.
Wouldn't it be 146 minus
37.
which would be 109?
No, I think 113. Okay, well, remember that if you're losing a 37, you're not starting from 146. 146 assumes that we have 35, 35.
Got it. So
148 assumes that we have 35, 37. And 150 assumes that we have 37, 37.
okay.
So if I'm starting from 146, then I only have 35 to lose.
Got it.
So I
that's
do
where
a
you get-
less than 35.
That's where you get that one, right?
If I have a 35 and a 37, and I lose a 37, or I should say, I'll still lose a 35, I still have a 37 attached. Or a 37, it would go here. With 2 37s. Good. Good, good.
Okay, thank you.
I have a question.
Yes.
So last week, or not last week, on Monday, you had us go and try to do something at home. And I wanted to know.
The NMR.
I was terribly wrong.
Oh, yeah. Nailed it.
Okay,
Great job.
I went through a lot of different ones.
Yeah, you absolutely nailed it.
Yeah, because it's that.
Yep.
Okay.
And I'll tell you what, that's actually harder than anything you'll have to do on your unit test,
Also, number
but you will have something like that.
on the active homework.
Yeah. Sure, let's go over it. You're welcome. You're welcome. You're welcome. Everybody get one? You're welcome. Tell me again which number, 13?
Yeah, number 13 on active.
On active for mass spec or and IR or NMR? Okay. I spent more time on mass spec than I meant to. It might be a good idea, but I want to have it pulled up so I can see it. How come I can't see it? This is strange. Oh, see, that's what I don't like. That's the form I don't like.
I honestly didn't look at the singlet versus quadruplet versus doublet. I looked at where
It makes me feel like I'm in student mode.
the
but I'm not.
Ring is the carboxylic acid. So it's like, okay, it has to have a carboxylic acid. And there's only one hydrogen right next to the carboxylic acid because it's the one singular.
There it is. Has it been 5 minutes? I think we're almost all back. So this is probably a good time for us to get going. All right, our last type of data analysis, infrared spectroscopy. We will call it IR. Think back to what you know about the electromagnetic spectrum. Is infrared light higher energy or lower energy than visible light? How do you know? You just have it memorized. You just know it's a lower frequency than visible light. It's below red. Who the heck knows whether red is high energy or low energy? I don't. I do, actually, but only because I've gone through this process. Do you know what the other end of the visible spectrum is? Violet. And what comes after violet? Ultraviolet, which we all know the energy of. Enough to break your DNA and cause damage and cause mutations and cancer, right? Ultraviolet is high energy, followed by violet. The opposite end of that is red, which must be lower energy. So infrared is lower energy than visible light. As it turns out, the energy of infrared radiation matches the transition between a low bond vibration and a high bond vibration, which bond vibration often translates into kinetic energy. And kinetic energy is thought of by us as heat. So infrared light is synonymous with heat. When you stand in front of a fire and you block some of that light, you can feel the heat is gone too. That's because you're not just blocking visible light from coming at you from the fire, you're also blocking infrared light. And that infrared light warms up the bonds in your face and in your hands. And when you block that IR light, you block the heat that comes with it. Wild stuff. Well, it turns out not every bond vibrates exactly the same. And the energy to change its vibrational modes is unique. So we can track what part of the IR spectrum is being absorbed and correlate it with the bond that absorbed that energy. There is a caveat, and that is that bonds have to change their dipole moment. So if a bond does not change its dipole moment by vibrating, then it does not absorb in the IR. And that typically means if a symmetric bond is happening, like oxygen to oxygen, O2, never sees a change in its dipole moment by vibrating, it does not absorb infrared light. But CO2 does have a change in dipole moment by bending. CO2 is a linear molecule. And so CO2 absorbs infrared light really well. So does water. Water changes its dipole moment by the OH bonds stretching. So it absorbs infrared light. Methane can stretch some of its bonds, the C to H, so it absorbs infrared light. Actually, water absorbs infrared better than methane and carbon dioxide. So when we talk about global warming, we talk about greenhouse gases, we're talking about heat being trapped in our atmosphere. That heat is infrared light that is being emitted by the Earth and caught by the molecules in the atmosphere and translated into kinetic energy rather than passing through the atmosphere. We see infrared light being caught the most on nights with a lot of water content because all of that water absorbs the infrared light coming from the Earth, warms the atmosphere. That's a naturally occurring process. It's what keeps us at a livable temperature. But the more we change the composition of the atmosphere, the more we change how much infrared light is transmitted through the atmosphere versus how much is absorbed, the more we change the temperature of the planet. That's the correlation here with IR. We're going to use IR on a much smaller scale than the environmental scale. And we're going to leverage it to figure out what bonds are present in a compound and what bonds are not. This is not the same type of deduction that NMR gave us. NMR told us hydrogen environments, but IR tells us bonding environments. The first example I gave you was the IR spectrum for penicillin. I think you can argue that penicillin is a crazy looking compound. It's got a lot going on. But its IR spectrum is actually pretty clean. It's got these nice, clean, Jordan doesn't agree. It's got these nice, clean absorption peaks. You'll see some others that are a lot crazier to look at. So IR spectroscopy leverages bonds absorbing in the IR region. The spectra that we're going to create have a y-axis that is percent transmittance. Think of that as how much light is being transmitted. 100% transmittance would give us our baseline. None of that light is absorbed. It turns out that baseline is always fluctuating. As something absorbs light, we call these absorption peaks. And I've had students in the past that struggle with the idea that the peak is not going up. The peak is going down. That's okay. Maybe you want to call it an absorption valley to help you get acquainted with it, but we're looking at light absorbed. Here, I've got peak absorption, the most absorption happening at that wavelength. And actually, our x-axis is given units wave numbers. Wave numbers is inverse centimeters. Are we analyzing wavelength or frequency when reporting wave numbers? It's the frequency calculated by inverting the wavelength. Wavelength, of course, should be centimeters, not inverse centimeters. Frequency is something per something. So this is a frequency because it's a per centimeter unit. It's just not frequency that we're used to seeing in terms of per second. This is a frequency calculated by the wavelength. When we plot this, we typically put 4,000 wave numbers at the left, and 400 wave numbers on the right. That means we look at high frequency light on the left, low frequency light on the right. Do you all have your correlation tables on you? Notice how big the IR correlation table is. How is the IR correlation table organized? What do you notice? Not absorption rate, frequency. High frequency range at the top to low frequency range at the bottom. That's one way to organize your correlation table. Other correlation tables will organize it by bond type because some bonds absorb in more than one way. Notice the very top one is the NH bond. And it says that this is a stretching frequency. The NH bond stretches between the N and H, and it absorbs in a high frequency range. Look closer towards the bottom, like 3 up from the black line, and we've got NH again. But this time it says NH bending. When the NH bond bends instead of stretching, that takes a different amount of energy, a different type of energy, and it absorbs in a different place. There are a lot of absorptions that are not listed on here. A lot. Which means when you look at an IR spectrum, this will not help you assign every single peak, because there are many absorptions that overlap with each other, and it makes it really challenging to pinpoint it to something. This is how we define the functional region versus the fingerprint region. We use 1500 wave numbers as our marker. The fingerprint region is between 400 and 1500. And a lot of bonds absorb here. You'll notice this black line on your correlation table. That separates functional from fingerprint. How many bonds are shown in the fingerprint region? 2. How does that agree with what I just said? These bonds only absorb in the fingerprint region, which means assigning these bonds to a peak is really challenging, because there will be a lot of other peaks in there from bonds that are not listed on here. Does that make sense? The black line marks challenging bonds to assign from easier bonds to assign. That's right. There's a lot of bonds that absorb here. On your correlation table, there are only 2 listed. Those are bonds that only absorb in that region and can't be found in the functional group region. Those 2 are competing with a ton of other things. So these are the 2 most challenging bonds to assign, because you don't know whether it's from them or from all of the other things that are absorbing down there. In the fingerprint region, we can typically break this up into 3 groups. There's I'm not going to do that as an X. I'm going to say that as a question mark. Things bonded to hydrogen. NH, OH, CH. All of your bonds to hydrogen show up in this high frequency range. Then we have triple bonds. Typically, this is carbon to carbon or carbon to nitrogen triple bonds. And then we have double bonds. Carbon to carbon, carbon to oxygen, carbon to nitrogen. But you'll notice I actually haven't put carbon to nitrogen double bonds on here. Maybe something that needs to be updated about this table. This is a selection of some of the most common bond types. Okay, so I want you to notice in that, and I know that I think my printer's dying, or my copier's dying, so I know that these are really hard to read. But I want you to see these 3 spectra. Are they different or are they the same? Different? I mean, I see a broad signal, broad signal, broad signal, and then kind of this sloped, pokey signal just to the right of it. Those look very much the same. But when you look in the fingerprint region, I've got this short, broad thing, taller, broad thing, kind of in the middle. When I look in this region, this is like 1100. I see nothing. I see a lot of peaks. I see nothing again. This is why we call it the fingerprint region. It's unique to every molecule. But the functional group region shows bonds that are much more identifiable. What do these all have in common, these three structures? Alcohol groups attached to alkyl carbons, sp3 carbons. I see the OH bond. Look at the correlation table. We're going to look in the high frequency region. Where do I see OH of an alcohol? 32 to 3400. And I see that for each and every one of these. About 32, about 32. Actually, these are all about 3300 wave numbers. Great. What's that other sloped and kind of pointy one? Also a CH bond. This is showing up just to the right of 3000. That's sp3ch. They all have sp3ch. So why is their fingerprint different? Well, because they have a different number of sp3ch, which can change how things absorb in there. There's also a CO bond in each of these, which only absorbs in the fingerprint amongst a bunch of other bond absorptions. And I know it's between 1000 and 1300, but it's really hard to tell what signal in there between 1000 and 1300 is actually caused by the CO bond absorbing. It's much harder to assign that in the fingerprint region. Now you'll notice that not all bonds are actually the same. So let's distinguish bond types. Is a CH bond a CH bond? No. An sp carbon CH bond compared to an sp2 carbon CH bond compared to an sp3 carbon CH bond are all different CH bonds. What's different about them? The orbital that's causing absorption. Is the orbital the overlap of sp with s, or sp2 with s, or sp3 with s? That changes the size and shape of the orbital overlapping with hydrogen. It changes the bond length, changes the nature of the bond. So they all absorb in different regions. Which absorbs in the highest frequency range, sp, sp2, or sp3ch? sp to ch, sp, ch, absorbs in a higher frequency than sp2, then sp3. And the alkene and the aromatic ring have a very similar absorption frequencies, so they get listed together. But there's another type of sp2ch that is distinct from all the others, and that's the sp2ch of the aldehyde. That's distinct still from the sp2 of the alkene and the sp2 of the aromatic ring. It's still an sp2 carbon, but it's a very different chemical environment, which changes how the bond behaves. What else? Are all OH bonds the same? No. You remember when I introduced functional groups to you, I said alcohols are different from carboxylic acids. Carboxylic acids don't contain alcohols. I can prove it to you now. The OH of an alcohol absorbs differently than the OH of a carboxylic acid. They're unique bond types. Okay, so I wanted to point out these two structures. One of these only has sp2ch. According to my correlation table, sp2ch absorbs above 3,000 wave numbers. That's a really nice marking line. The distinction from sp2 to sp3 lies right at 3,000 wave numbers. The compound on the top has a lot of sp2ch, but it has 2 sp3 hybridized carbons. So one of these molecules should show me CH absorption from sp2ch and sp3ch. One of them should show me only sp2ch. Can you tell me which of these two spectra contains both types of CH bonds? I know those numbers are really hard to see, so I'm going to tell you that this right here is 3,000. That second number from the left, that's your 3,000 line. That's the distinction line between sp2 and sp3ch. Which of these contains only sp2ch? The one on the right contains only sp2ch. So when I look at 3,000, I see absorption to the left and to the right. But my left structure, my left spectrum, I mean, when I look at 3,000, I only see absorption to the left. I don't see an absorption peak to the right. The structure on the left, only sp2ch. Only absorption above 3,000. The spectrum on the right has both sp2ch and sp3ch.
And when you say to the left and right, you mean like immediately, right? Because the other ranges are picking up other...
Well, I can't go too far. That's right. And I even have a range here that says sp2ch is from 3,150 to 3,000. That's a pretty small range. That's this. And sp3ch is 3,000 to 2,800. That's also a small range. So you're right, we're looking at immediately past that 3,000 line. By the way, I can't do this on my board or my screen, but I would circle this set of peaks to the left, circle this set of peaks to the right. Label them as not just CH, because they are different CHs, sp2ch, sp3ch. Over here, sp2ch only. So by the way, this is naphthalene on the bottom and dihydronaphthalene on the top. Naphthalene belongs to the left spectrum. Dihydronaphthalene belongs to the right. And I forget about my alcohols, but I think it was 1-butanol is on the top. The methylbutanol is on the bottom left, and then the dimethylbutanol is on the bottom right. Not that it matters, because you wouldn't be able to discern that by analyzing the bonds that are there. You'd have to be able to distinguish the functional group region. All of that to say, IR can't always give you structural determination. All it can tell you are the bonds that are present. Sometimes it can't even give you functional group. All it tells you is the bond that is present. And sometimes we can correlate that to the functional group. I want to point out that different bonds will give a different number of peaks, a different intensity to their peaks, and a different shape to their peaks. Now, I have given on my correlation table shape and relative intensity, and every now and then I say 2 or 3 peaks. A lot of times, this varies. The intensity that we see is a relative intensity. It's not even a specific intensity. It's set relative to that spectrum. So the intensity that appears medium for one compound might appear weak in the other compound, might appear strong in a third. The shape sometimes changes based on the concentration of the sample. The number of peaks in an absorption might change. Okay, so for example, let's compare butanal with 2-phenyl 2-butenal, right? Butanal should have the CH of an aldehyde. My correlation table tells me the CH of an aldehyde shows up at 28 and at 27. That's not a range. Those are two specific values. And it tells me 2 peaks. Okay, here is 3,000 at that dotted line. 29, 28, 27. Here's 28 and 27. 2 peaks. And just left of 28, but between 3,000, sp3ch, which my compound has. I'm seeing sp3ch followed by these twin peaks of the aldehyde at 28 and at 27. My next compound doesn't give me as clear information about sp3ch. How did the CH bond go from very intense to very weak? It's a different compound, and it varies a lot. But I still have an aldehyde, so I should still have a signal at 27 and at 28, and I do. The CH of the aldehyde always has those 2 peaks. But this second compound also has sp2ch, which shows up to the left of 3,000. My first compound did not have sp2ch. No signal to the left of 3,000. There's some other signals in here as well. And this is where I want to get to with the next one, corresponding peaks. We look down in the 1700s, or teen hundreds. This is about 1650. This one is about 1710. I see these strong signals. What does that correspond to, given my correlation table? Teen hundreds, it's all carbonyls, CO double bonds. And my aldehyde has a CO double bond. So I can correlate this signal at 1650 and at 1710 as the CO double bond. And in fact, my correlation table tells me the CO bond of the aldehyde absorbs in that range, 1740 to 1660. It can show up anywhere in that range. And this is something for us to look out for. Corresponding peaks. I get this a lot from students. They'll say, I have an aldehyde in my compound. So I predict the aldehyde, which we can show as RCHO, should absorb at 2800 and 2700 wave numbers. That is not true. Well, it's not enough. The aldehyde does not absorb there. The aldehyde is a carbonyl CO double bond bonded to a hydrogen. I need 3 atoms, 2 different bond types to describe an aldehyde. 2 different bond types, but IR is looking at specific bond types. The aldehyde does not absorb there. The CH of the aldehyde absorbs there. The CO of the aldehyde absorbs somewhere else. So saying CH is not enough, saying aldehyde is not enough. It's the aldehyde CH that absorbs there. The aldehyde CO, according to our correlation table, shows up anywhere between 1740 and 1660, and that is a bit approximate because here we're seeing it around 1650. So it seems a bit out of that range, but it's close.
Can you remind us what this paper looks like on our, because you
Yeah.
give us part of it, but
The only thing you don't get on the exam is the far left column. So you have to know what these bond names mean, but you don't get to see what it looks like relative to a structure. You also get the NMR, but you don't get any words. You just get the structure, which is probably easier. Corresponding peaks. How do you define your functional group? All of those bonds should have a peak. What is an alcohol? Carbon to oxygen to hydrogen. OH is one bond, and if I see that somewhere, I should also be able to find a CO bond. How do you define a carboxylic acid? And that's the structure we have here. A carboxylic acid has both the CO double bond and the OH attached to the carbonyl. The correlation table says the OH of a carboxylic acid is quite different from the OH of an alcohol. This has a very broad absorption. Whoop, there it is. You see how broad that absorption signal is? Why is it that the OH bond can absorb at so many different values, but all of these other bonds seem to absorb at very specific values? Hydrogen bonding between groups changes the nature of the bond, changes how it can absorb. And carboxylic acids already have some unique characteristics going on in their OH group. So they get this very broad region of absorption. These two structures are isomers of each other. This is butanoic acid and ethyl acetate. They have the same chemical formula. And they both show evidence of a CO double bond. This is about 1740 or 1720, and this is about 1710. My correlation table says that that range could be ester, carboxylic acid, ketone, or aldehyde. A lot of different CO bonds that could be there. Here I have a CO bond. If I think it's from a carboxylic acid, I better be able to prove that there's the OH of a carboxylic acid. And there is. On the right, I have a CO pi bond, CO double bond. If I think this is from a carboxylic acid, I better see a broad absorption from the OH, and I don't. If I think this CO pi bond could be from an aldehyde, I better see the CH of the aldehyde, and I don't. If I think that this is from an ester, then I better see the CO single bond of the ester. Bummer, because the CO bond shows up in the fingerprint, and it can be really hard to ascertain which of them it is. In this case, though, it's this very strong signal in the fingerprint, which tells me that this CO double bond is more likely an ester than it is a ketone, because a ketone would not have a corresponding CO single bond. That's what I want you to take away from corresponding peaks. If you're going to tell me you have an alkene functional group, I want to see the CC double bond, which shows up around 1600, and I want to see the sp2ch, corresponding peaks for your functional group. If they're not both there, it's hard to validate that it is really that functional group. And of course, then I have to follow that up with saying that sometimes the bonds just don't absorb well. And so that functional group might be there, but that bond is just not absorbing well, and it's hard to validate. So this is where I wanted us to put it all together. On your unit test this weekend, you will have to put it all together. You'll be given a chemical formula, an IR spectrum, and an NMR spectrum. IR is great because it helps you figure out what bonds are present. NMR, after that, tells you your hydrogen environments. Putting it together, IR gives you functional groups. NMR tells you how those functional groups are arranged. Now you can build its structure. But most importantly, degrees of unsaturation. If I know a chemical formula, I can calculate the degrees of unsaturation, which tells me pi bonds and or rings. If I know there could be pi bonds, I can start looking for pi bonds. And if I don't see evidence of pi bonds in the IR, then it's probably a ring. If I have evidence of pi bonds, that narrows down my functional group. So when I look at the NMR, I can validate those functional groups. Then I can start piecing them together. So I want to do this one. This has a chemical formula, C8H16O2. I'm running out of time, so I'm going to do the degrees of unsaturation for us. Two chicken rule. There are no halogens, there are no nitrogens. 16 minus 16, 2 divided by 2. I have 1 degree of unsaturation. Is it a pi bond or is it a ring? I'll look at the IR first. Here's my IR. Evidence of pi bonds would be from 1500 up to about 2300. I've marked 15 with this dotted line. Here's 2200. I see a pretty strong signal there. This signal is 15, 16, 17 something. What absorbs around 17 something? CO double bonds. Is it the CO double bond of a carboxylic acid? If it is, I should see a corresponding peak for the OH. Evidence of that broad OH of the carboxylic acid? No. Is it the CO double bond of an aldehyde? If it is, I should see twin peaks at 28 and 2700. Do I see twin peaks? Not really. Certainly not ones that look like the others. If it's a ketone or an ester, the only way I can distinguish is by the CO bond. And that can be really hard to discern here in the fingerprint region. But the NMR would be able to tell me a difference. The NMR says an ester will have hydrogens close to the oxygen that show up around 4 ppm and close to the carbonyl that show up around 3. The ketone has no oxygen close hydrogens. The ketone would have 2 versions of hydrogens close to the carbonyl. So it would have no signals close to 4. Let's look at the NMR. Ooh, a signal close to 4. That gives me evidence that there's hydrogens close to an oxygen. That might just validate my ester theory. This, by the way, is a much more challenging version of a problem. You're not going to see something this hard on your exam. There's too many structures, too many carbons. This is really hard to ascertain the information from. 9H, 3 methyl groups. But they don't all look consistent. So I'm going to say that these are not a tert butyl, but this is 9H from 3 different methyl groups throughout the structure. A 1H, a 2H close to a carbonyl, a 2H close to an oxygen. Do you guys want me to just give you the structure? You would have gotten there. And you know what? I think I'm short on my hydrogen count. 2, 4, 5, and 9 is 14. So I think I mislabeled the integration anyways. Sorry. I think if I had labeled this better, The 9H should have actually been labeled as 11H. Again, that was harder than I meant to give you. Look at the mass spectrum. Evidence of bromine or chlorine in the compound? I don't see any isotopic clusters, 1-to-1 or 3-to-1. So the mass spec kind of confirms that there's no bromine and chlorine. That's the most relevant part. But now that we've predicted this, can we predict a molecular ion for this structure? Yeah, easy. Pull out one of the lone pair electrons, leave a radical cation. Pull out one of the pi bond electrons, leave a radical cation. That's what I'll have you do on the unit test this weekend. Predict a structure, regardless of whether you predict it right or not, predict a molecular ion for that structure. Okay? Oh man, I'm taking you way over, but Jordan brought up earlier that I didn't solve this on the NMR on Monday. So I wanted to give you guys the structure to that last C5H10O2, which was a carboxylic acid and an isobutyl group. 1H in the carboxylic acid range of the NMR, 2H adjacent to the carbonyl, 1H that has 2 methyl groups next to it, and 6H, 2 identical methyl groups. And if you guys have the time to stick around, I wanted to answer, whose question was this? 13 on the NMR problem on active. We've got a chemical formula. Can we calculate degrees of unsaturation? Yes. 6 minus 7 plus 1 plus 2. So 2 divided by 2. 1 degree of unsaturation in this compound. The IR shows me signals to the right of 3000. What bond is that? sp3CH. It shows me nothing around the carbonyl range, no CO pi bonds. But then I've got a strong signal at 1550 and 1350. What does the correlation table say for that? The nitro group, NO2. Now, we don't actually go through this group a lot, but the NO2 group looks like this. How many degrees of unsaturation there? One degree of unsaturation from the pi bond between N and O. And then we have our structure. Looks like we've got something that is functional group adjacent, CH2. Something that is not really functional group adjacent, CH2. And something that is at the end of the chain, CH3. I imagine the hardest part of this for you was figuring out the NO2 group. Well, you don't need to either, because I think when you draw the structure, they actually give you the option to do NO2. So you don't have to draw out the NO2 group. Yes, it does.
Oh.
It's just assumed.
Okay.
This is NO2, just drawn out.
Things, and I was like, there's no way to not, or to like make only 3 bonds to nitrogen. Because isn't it typically just 3
Yeah.
bonds to nitrogen?
Typically, if it has 4, it takes on a positive charge,
Yeah. But that's
which
what
is
I
balanced by
didn't-
the negative charge.
Yeah, that's what I didn't know, is that like you could do the charges.
Neutral. Yeah,
Sweet.
it does suck.
Yeah, that makes more sense. I understand.
The NMR should have given you CH3 bonded to CH2, bonded to CH2, bonded to some functional group that is shifting that signal so far to the left. Do you agree? Look at the NMR again. CH3, wow, that's really great. 2 neighbors. CH2, 5 neighbors. It's got 6 peaks. CH2, 2 neighbors. The only way you can have that is CH3, CH2, CH2. And then that CH2 has to be bonded to the remaining nitrogens and oxygens. And it is the NO2 group. All right. Thank you guys for your time. You're going to do great on this unit test. The feedback I've gotten in the past is that part B is not as hard as it felt today. So by the time you've gone through part A twice, you should have solidified your skills on NMR, IR, and mass spec and putting them together. That part B should feel pretty doable. I'll see you guys on Monday for our midterm review. Have a good weekend. Come with questions on Monday.